About the pseudo-spectral method, let me quickly show you first a few motivational slides why actually the method is very popular. And the method can be used, for example, to calculate how galaxies move. So dynamics for galaxies. You see this slide. Did it change? So you see the galaxy you have. So there's spiral arms, etc. And then the galactic dynamics, you can use a pseudo-spectral method to compute that. And the advantage of the pseudo-spectral method is it is a very highly accurate method to solve your partial differential equations. And so whenever you require a highly accurate method, then the pseudo-spectral method is your method to go to. Another one, for example, where it's used is for the Boltzmann equation. It's the one you see here, which describes basically like the statistical behavior of a system in terms of the thermodynamic characteristics of the system. So again, with a highly accurate method, you can look into these systems from a thermodynamic point of view and solve the Boltzmann equation with it. Or, for example, in quantum theory, if you're looking for structures, optimized structures, for example, for molecules, like organic molecules, based on the so-called density functional theory, DFT theory, again, you can use the pseudo-spectral method for these kind of studies. And another one based for quantum systems is the Schrödinger equation. I don't know if you saw this when you study physics. Is one of the equations you will see at some point, which describes the quantum state of a quantum system. And again, the pseudo-spectral method, for example, is used to solve these equations. And then also where it's very popular is in fluid dynamics. So where you have these air turbulences, for example, that's again an application where you want to have a high accurate method. And so the pseudo-spectral method is very suited for that. And also the Navier-Stokes, we saw that from the shallow water equations, which derive from the Navier-Stokes equation. And the Navier-Stokes equation you can try and solve numerically as well with the pseudo-spectral method, for example. And then it was proposed also for seismic wave propagation, maybe in the 90s, quite a few years ago. And again, it's obvious you want to have a highly accurate method. And so the pseudo-spectral method was proposed to solve the wave equation. And that's something we want to come to in then the homework about this method. Basically, we want to look at the wave equation and then solve it with the pseudo-spectral method. So that's the goal, basically, what we are after here in this class. Now, instead of going through these slides, so let me stop here. And then let's discuss the lecture notes. I have a few points I want to mention. Just to give you the basic idea behind the method, how it basically extends the finite difference approach that we looked into so far. And then give you also maybe a quick derivation of its dispersion behavior, for example. We looked at stability analysis for the finite difference methods. And then also we're touching to the numerical dispersion effect, such a method. I can give you here as well a derivation of the dispersion effect for the pseudo-spectral method this time. And then you can compare, for example, with the finite difference approach. So good so far? Shall we do that? Good. So from your notes, let me see if I can quickly give you the main points. And the main idea behind the method. Let me try and do this here with the iPad again. Let me see if I can share that. Good. So pseudo-spectral method. So the main idea basically is that we use as much information from the grid that we have as possible to come up with a stencil, if you want, which is as accurate as possible. So you saw it from the finite difference method. So let me quickly put that down. Let me consider the center difference. Infinite differences. Then we have the derivative of the function, let's say the spatial derivative. Oops. That we can approximate or write as the evaluation of the point next to the one that we look at. So the two neighboring points divided by this grid space 2 times. And then this is a second order scheme. So the truncation errors and second order. And so here, if you want to plot the stencil, so we evaluate at point n, and the information that we would need in this case is at n+1 and n-1. So that's the finite difference stencil basically. So that gives us the partial derivative at position n. And in this case, when we use this center difference scheme, it's second order accurate. Now, last time you saw, for example, when we go to higher order finite difference schemes, the stencil becomes wider when we increase the order. So we need more information from the neighboring points. And that helps us to increase the order. So the idea now of the pseudo-spectral method is what if we now use the information from all grid points. So if we use the information at more positions, so we can increase the order of accuracy. It's basically the observation that we have from the higher order finite difference schemes. So the idea behind pseudo-spectral methods is why not use all the points. So now we basically have some domain 0 to L, which we discretize with points. And for some position N, we basically want to use all the other point information. That will give us the highest possible accuracy of the stencil. That's the main idea behind the pseudo-spectral method. So just use all the grid point information in order to get a method which is as accurate as possible.
Professor, can I ask a question?
Yeah.
In this method, we use all of the point, but infinite difference, we find another point. So how we can get all the point before we find the next, I mean, all of this point? Infinite, we find the next neighbor point, right? But how we find all, we use all of the point in this spectral, how we get the value of each point, basically.
Well, let's say for a time n, we know what the wave field is on the whole grid. And now we want to approximate the solution for the next time step, n+1. And for this next time step, n+1, we have the information of all the grid points, the wave field at all grid points.
So we have to know all of the value of the n first.
Yes. Yeah.
Okay.
That's the idea.
Okay.
So if we have that information available, why not use it?
Okay. Thank you.
So, Professor, you mean that if we want to compute every point of time and t+1, we have to use all the position informations of time t, right?
Yes. Yeah.
Okay.
And maybe even previous times, depending on the time scheme a bit. But we will focus here on the spatial derivative.
Okay.
For the time derivative, we still use a finite difference approximation, like this central schemes for the time derivative. We stick to that, we leave that, but now focus on the spatial derivative. And for the spatial derivative, we want the highest accuracy now. So that's basically the goal now. Use the pseudo-spectral method just for the spatial derivative, but still use the finite difference stencil for the temporal derivative. And then combine these basically. So you saw from the finite difference higher order schemes that when we add more points, the stencil becomes more complicated. The approximation becomes quite tedious actually to write down. If you would do it now for 8th order or 16th order, then your stencil becomes very wide. And it is quite tedious to keep track of all these single terms that come out of the approximation, the finite difference of stencils. So the tool that we use for the pseudo-spectral methods, the major, let's say, workhorse that we're going to use is the Fourier transform. And that's why we have this little excursion into Fourier transforms in the lecture notes.
So we build a signal for specific time, if I'm not mistaken, as an input in order to implement the Fourier transform, or not?
Forget time. At the moment, we're just in space. We're just in a space domain, and we want to find the highest accurate spatial derivative of a function.
Okay.
So yes, Fourier transform you can have in a time domain, but also in a spatial domain. Let me quickly. Remind you of that. So this is one of the major ingredients for the pseudo-spectral method, the way we present it here. So there are variations of pseudo-spectral methods which don't necessarily need Fourier transform. They use other transforms. But the most simple way of introducing you this pseudo-spectral method is through these Fourier transforms. I can quickly put this down. So the Fourier transform, probably you have something in your notes. As an operation which transforms one function from one domain let's this function with small f to another domain. Well, we say the function becomes capital F. And so our focus is on the space domain, the spatial derivative. That's the focus. So what is the Fourier transform giving you when you transform a function in space? In which domain do you end up, the Fourier transform?
Frequency domain.
Not frequency.
Wave numbers.
There's a wave number domain. So that gives you the wave number domain. I think, Tad, you are still thinking of Fourier transform in the time domain. So if we have a function of time and we take the Fourier transform we end up in the frequency domain. Then we have the capital function f, which is a function of frequency. But again, for us, the pseudo-spectral method, we want to find the spatial derivative. So we will be in a space domain. When we take the Fourier transform of a function which varies in space, we have then another function, capital F, which is a function of wave numbers. So we go from space domain into wave number domain and then going back basically again. So the transform and the inverse transform are needed for us to go into the wave number domain and come back. Basically. You have that, so the operators for Fourier transforms and inverse Fourier transforms. So we can write the Fourier transform ft as fk. Now that's our function in the wave number domain. Is this integral of our function in the space domain f of x times e minus ikx integrated over x. That would be the Fourier transform. That brings us from a space domain function f of x to a wave number domain function f of k. And to go back, we have the inverse Fourier transform that brings us back to the space domain function. And if we define the Fourier transform as this integral, then the inverse Fourier transform has this factor 1 over 2 pi in front of the wave number function f, capital F of k, times eik x integrated over all wave numbers dk. So here, k, that's the wave number, and x, that's a spatial position. Good, and what you note is the derivative. So take the derivative of our function. So what we are interested in is the derivative of our function. If you look at the above expressions for the Fourier transform, the derivative is basically 1 over 2 pi, the integral ik times fk times eikx dk. So if we write that a little bit in a different form, we can see that the derivative in the wave number domain is simply multiplying by ik of, sorry, that's fk for our wave number domain function is equivalent taking the spatial derivative of our function in the space domain. So you see this is wave number domain. Taking the derivative is much simpler in the wave number domain than in the spatial domain. So what we do in order to find an approximation to the derivative, to the spatial derivative, we transform the function with the Fourier transform into the wave number domain. Then take the exact derivative, but just multiplying with ik, and then transform it back into the space domain.
Professor?
Yeah?
Does it mean equals here in this equation? Does it mean ikfk equals the derivative fk in terms of x?
Not quite. You have, see this one, this would be the expression of the derivative. It just means taking the derivative in the wave number domain is simply a multiplication by ik, the function. But
I guess it might be fx, not capital Fk.
So if you want, the derivative would be the inverse Fourier transform IFT of our IKFK function. Then this would be equal. So it just means the equivalent of the derivative in the wave number domain is multiplying by ik. Well, the actual derivative of this function in space domain is then still taking the inverse Fourier transform of that product.
Okay.
But you see where the method is going, basically. The method, in order to achieve the highest accuracy, it takes the information from all points. And for the derivative, in order to approximate the derivative, it goes into the wave number domain, where the derivative is mathematically done exact by multiplying with ik. And then goes back with the inverse Fourier transform into the space domain. So if you want, the derivative itself is not approximate, it's mathematically exact, but the approximation comes from the discrete Fourier transform that we need to apply. So since we have a discrete number of points, we cannot do the continuous Fourier transform, but we have to do the discrete Fourier transform. And that is then where the approximation comes into the effect. So if we would have an infinite space, an infinite number of wave numbers, and if we could do the continuous Fourier transforms, then we would be exact. Then it's mathematically equal. Take the derivative in space domain or wave number domain. But the approximation of the spatial derivative comes in by using then the discrete form of the Fourier transforms. So the discretization it happens with the discrete Fourier transform. And that's given by, you have the formula. It's a bit tedious to write down, but let me see. So F, now the wave number is a discrete wave number. It's a KL, which we can write as L times wave number increment delta K, which then is this sum from n0 to n minus 1, F evaluated at the grid point xn times E minus I k n or Lxn. This is KL, sorry. Times delta x. So I can write out these terms a bit. Xn is now n times delta x. KL is L times delta k times n times delta x, that's xn times delta x. And if you want, let's take that delta x in front of the sum. And we have the sum from 0 to n minus 1 of our function evaluated at the grid points times E exponential function minus I 2 pi n L over capital N. That would be the discrete Fourier transform. So we had xn is n times the special increment delta x. The wave number, discrete wave number KL is L times the wave number increment delta K. And these indices n, they go from 0 to n minus 1. And L the same to n minus 1. So this would be the discrete Fourier transform, and then we have to go back, basically, take the inverse Fourier transform, and similar to the forward Fourier transform, you would have the inverse then can be written in a discrete form. And we go back to the spatial function, evaluated at grid point xn. That becomes then this expression. You have it in the notes as well. Now we go for the sum over all L, and this is L delta K times E I 2 pi and half N L over N. That would be the inverse Fourier transform, again the discrete one. So with these two formulas, we can then basically go back and forth for our discretized domain. So that's the discrete inverse Fourier transform.
Professor?
Yeah?
I think there is a typo in the notes. In the
Go, let
Zoom.
me find the notes. Yep.
You are the inverse Fourier transform is the sum is over n and it should be so over L. This is
Yes,
the
you're
page.
right. Yes.
Okay. Thanks.
Yeah, the inverse is summing over the L indices. So it's basically the sum over all the discrete wave numbers, the KL wave numbers. So you can write the KL wave number as L times the delta K increment. So it's the sum over L. Yes. Thanks for pointing out. You can correct that. So what would be the derivative now? So putting this together, we can find the derivative of our function evaluated at grid point xn, which is n times delta x, becomes then the inverse Fourier transform of the wave number function multiplied with ik. So let's write n delta x. Then we have the sum over L to n minus 1. And now we have these products of I times KL, the discrete value, which we can write as L delta K, times our wave number function, L at position KL. Then we have the exponential function that brings us back. Can write as I times 2 pi n L over capital N. So this is now how we evaluate the spatial derivative of the function. We do the discrete Fourier transform that gives us this part. Then multiply with ik, which is this part. And then take the inverse Fourier transform to go back into the spatial domain. If you want, that's ik, that's fk. So you see how this would look like for the discretized domain. If you want, look at the Fourier transform, the discrete Fourier transform, which we need to do. So f of KL is now a function where we need to have all these grid point informations. So f evaluated at all grid points xn. So you see that we need all the grid point information of the function for the discrete Fourier transform in order to get the wave number function. We multiply this by ik and then do the inverse Fourier transform. So it does indeed take the information from all the grid points in order to take the derivative of the function. So you're probably all familiar with the Fourier transform. And you know the Fourier transform behaves well for periodic functions, but unfortunately it doesn't do so well for non-periodic functions. And so when we take the Fourier transform for our derivatives, there is an issue with the boundaries of our domain. So in principle, by taking the Fourier transform, we would consider the boundaries as having periodic boundaries. So the function would just keep on repeating itself periodically at the boundaries. But since we truncate it, this leads to issues with the Fourier transform. So which means that this method has issues with the boundaries.
This is the Dirichlet necessity or not?
Say it again?
This is the Dirichlet necessity or not? The weak Dirichlet. No.
With both type of boundaries. But in particular with the Newman boundary. Because the Newman boundary has non-zero values at the boundary, which for a Fourier transform would then give like a non-periodic boundary where it's non-zero at the boundary. So it's an issue mostly with boundaries where you don't just have zero displacement, but where you have some displacement at the boundary, which, for example, the free surface is such a boundary. So pseudo-spectral methods, they do have an issue with the free surface conditions, for example, in seismics. It's not a very big problem if you have absorbing boundaries all over your domain, because then you basically can just extend your domain. But as soon as you want to implement a free surface boundary, then we will have issues with the Fourier transform. I can quickly give you some note at the end that in order to work around this, people were looking for other transforms other than the Fourier transform. And so what they found is a very convenient transform is the Chebyshev transform. So now you have basically a domain with a free surface on top. Then you do a Chebyshev transform in depth and keep the Fourier transform for the lateral directions. So then you basically have this combination of Fourier transform and Chebyshev transforms. And that has has been shown that this is quite a powerful combination when we want to model seismic waves with a free surface.
This is a similar issue when you apply a filter and you have to taper the boundaries.
Yes.
Or is yes?
Yeah.
Okay.
Yeah. Yeah. So I can put down a little note about the boundaries. Can be an issue. But the advantage is that we reach a very high accuracy. Of the spatial derivative. So do you have questions about that, about the notes you were reading with these additional points that I added? So the idea is clear of the pseudo-spectral method. So we focus on the spatial derivatives. So we want to have the highest possible accuracy, basically. And one way to achieve that is by using the Fourier transform, which considers the information from all grid points in order to achieve the highest possible accuracy. Because the derivative is in the wave number domain, which is mathematically exact. But then the approximation comes in with discrete Fourier transform. Once we discretize, we have the discrete Fourier transform, and that's the numerical error that we introduce then into the derivatives.
Why don't we use Chebyshev all the time instead of changing into between?
You could use Chebyshev for all special dimensions. It's probably just because the Fourier transform is a very convenient transform. So if you don't need to deal with the boundaries and don't need to deal with the free surface, then the Fourier transform is like the a natural way of introducing that. Because you see, it's mostly due to this effect that the derivative in the wave number domain is exactly ik, the function. So yes, there are like pseudo-spectral methods which use different transforms, but let's say the easiest way of introducing it is by using the Fourier transform, and you see why it's the Fourier transform because of that spatial derivative behavior of it. Do you have some more questions from your notes that you were looking through? clear with the discretization? It's also mentioning it what, for example, the largest wavelength can be, which is determined by the extent of the domain that we look at. Which also gives you basically a relation to the small increments that we can have. So the delta k, basically, the wave number increment is determined by how we choose the grid spacing, the delta x. You have that, if you want, you have the wave number increment is then equal to this factor 2 pi over n times delta x. So it's the size of the domain and the spacing delta x, which determines then what the wave number increments can be. So, good. Then the second point is about the dispersion, the numerical dispersion, the pseudo-spectral method. You have that as well in the notes. So I can keep this short, probably. So let me quickly give you the main points here. Well, the example that we have is the advection equation. Which we can write as time derivative of u is then equal to this minus c times the spatial derivative. That would be an equation which describes the advection. And this equation is used for the dispersion analysis in the notes that you have. So we see then for the time derivative, we use a finite difference scheme. So we approximate this by this m plus 1 minus u m minus 1, a central scheme, divided by 2 times delta t. That would be our approximation of the temporal derivative. Is then equal, and now we use the pseudo-spectral scheme for the spatial derivative. So we have this factor minus c in front. And then we have here the derivative, which is still given you at the top here of the page. So we have this 1 over n times delta x summing over L, 0 to n minus 1 times I L delta K. And then we can write this capital U as the wave number domain function at time m at position L delta K times this exponential factors 2 pi n L over n. So this capital U here function, that's our Fourier transform of our small function in space domain at time m, um. So the right-hand side we evaluate at time m, and on the left-hand side you have a simple central scheme, finite difference scheme for the temporal derivative. So you can put this together then, and what we are looking for is basically the stability condition. So you have the whole derivative in the notes. And the stability condition we can see easily when we look at the sign of then omega delta t, which is this factor 2 pi c delta t over delta x times L over n. And so the sign function has to be smaller than 1, which means this basically has to be smaller than 1. And that gives us now a condition on the time step. So if you want, then we have c times delta t has to be smaller than delta x over 2 pi n over L. If you want, c delta t smaller than delta x over 2 pi, since L is smaller than n. That's our stability condition. So the advection equation, when we use the pseudo-spectral method, leads to the stability condition for the time step delta t. If you want, compare this to a finite difference evaluation of the advection equation, we would find a condition which would be c delta t over delta c times delta t has to be smaller than delta x for finite differences. Let's say when we use a central scheme instead of the pseudo-spectral scheme for the spatial derivative. So you see the pseudo-spectral scheme leads to a slightly smaller time step. So it has this additional factor 2 pi in the stability condition compared to the finite difference scheme. That's the stability, and then you also have the the dispersion, so the numerical dispersion for this method then becomes that the frequency of a given wave number signal, frequency at KL, depends now on the time step size, 1 over delta t times the arcsine of C KL delta t. And since KL is controlled by delta t as well, you see here with the above equations, we see that in this case the numerical dispersion is controlled only by delta t. The spatial, the temporal increment, and not by the spatial increments. So the numerical dispersion is slightly different for a pseudo-spectral method than for a, let's say, finite difference method. By delta t compared to finite difference schemes where the numerical dispersion is controlled by both, compared to finite difference schemes which depend on delta t and delta x. So in principle, the pseudo-spectral method is highly accurate, and the numerical dispersion is controlled only by the time step size that we choose. Good. Do you have question to that? It's mostly done just to point out the difference to the finite difference schemes that we looked before. So we take a simple example here, the advection equation, look at the stability condition, compare it to finite difference schemes, and look at the numerical dispersion of such a discretization. You have in the notes again how you basically would do the analysis by assuming this plane wave solution for U, stick that into the discretized form of the equation, and then you basically end up with these conditions and numerical dispersion equations. So it's one way of analyzing it. Yeah. There are a few more points that I usually will give when we look at the pseudo-spectral method. You have them in the notes some. So let's say first point is the Fourier transform makes the boundaries periodic. And that's why, for example, then people use non-periodic transforms like the non-periodic Chebyshev, for example. Has been proposed. But again, the Chebyshev transform imply that the surface is flat. Cannot account for topography, for example. So then you would have Chebyshev transform in depth. And the Fourier transform for example, laterally. That's one remark. Another remark is about the computational aspect of the method. Regarding the computation performance. Now the Fourier transform, it has long been a transform which wasn't very suited for computational calculations until basically the fast Fourier transform was proposed. And the fast Fourier transform, the FFT, made now the Fourier transform suitable for computational applications. Still, there is one drawback in using the FFT, and that means that for each grid point evaluation, we need to have the information from all other grid points. Then we can do a Fourier transform. So if we start discretizing the domain, say we need to run it on multiple processes, we want to parallelize it. So basically, for each evaluation, we need to gather first the information from all the other processes. So there is a lot of communication involved, basically it's all to all. If we stay in this process, we need to share the information from our domain to all the others and need to gather the information from all other processes in order to compute the FFT for a singular point in our domain. That makes it very heavy in terms of communication. And so the pseudo-spectral method suffers from that communication overhead. And as soon as we start parallelizing and want to run like large-scale applications with the pseudo-spectral method, it becomes not very efficient anymore, because most of its time it's wasted by the communication overhead rather than doing an actual computation. So keep that in mind, basically, the pseudo-spectral method. involves all points in one direction. And so this usually is a bottleneck. For parallel computations. Computations, especially when you go to 3D application, large-scale applications. So there is work done on trying to improve that, basically make pseudo-spectral methods feasible for also large-scale and 3D. But it still is a very challenging aspect to parallelize basically the FFTs. And then final point is about the grid points per wavelength. So when we use finite difference schemes, it depends on the order of the stencil, but like a rule of thumb usually is that you need between 5 to 10 grid points per wavelength that you want to simulate. We see that it's also more or less the number of grid points when we go to a finite element method or the spectral element method. It's 5 to 10 grid points per wavelength that we want to simulate. Now for the pseudo-spectral method, in principle, that can go down to only 2 grid points per wavelength. And we can already resolve that wavelength. So let me quickly put that down. So the number of grid points per wavelength, the signal that we want to simulate for, let's say, typical finite difference. This is typically between 5 to 10. So that is the smallest wavelength that we can resolve. This lambda minimum is around 5 times the grid spacing that we have. Now with the pseudo-spectral method, together with the Fourier transforms, and in principle this can go down to 2. So that means we can basically achieve with the same grid, we can resolve higher frequencies when we use a pseudo-spectral method. Or if you want to achieve a certain minimum wavelength for your simulation, we can choose a coarser grid when we use a numerical or when we use a pseudo-spectral method. compared to a finite difference approximation, for example. Good, that's it. It's basically all I wanted to give you as a home message. Do you have any questions, any remarks? So more or less clear how the pseudo-spectral method works? So, given that we have to conclude, we will discuss the homework next Thursday. So we will meet next Thursday again, and then just basically look at the homework for the pseudo-spectral method. When you have to code it up, it's actually simpler than it looks maybe from a theoretical point of view here. But we will code up this little example with the wave equation using the pseudo-spectral method. And so we can discuss that next Thursday, look into that new homework, and then yes, they can work on it for then the other week. Is it good? Does it work for you?
Yes.
It's good.
Very good.
And about the method, you have some more questions?
No.
Let me stop sharing here. Did the lecture notes help you when you go through it and look now at these main points that I gave you? Were they helpful or were they difficult to understand, to get it?
It was helpful.
Yeah, it's very helpful. But I think I need to read from the textbook for this method also.
I agree,
Yeah, you
Professor.
can. Yeah, go ahead.
Yeah, I agree with them. This news is really helpful, and it really helps me to think more or think deeper. Then I can ask questions about them. Yeah. So if you like, I'm wondering if you can, if it's possible, then you can set us the notes before the class. Yeah.
Yeah, I put these notes as well in the GitHub repository. So you also
Okay.
have these notes.